Howdy. So what have we learned? We've learned that the change enthalpy of a reaction can be calculated using standard enthalpies of formation by doing the products minus reactants things, or using Hess's law. Remember, if you add a series of reactions, you add the corresponding delta H's. We've also seen that the change in enthalpy is equal to the amount of heat transferred to the system under constant pressure and assuming only expansion work. This video is on the different types of enthalpies. So different types of enthalpies, like enthalpies of vaporization, fusion, can be used to calculate how much heat a system absorbs or emits. The size of the different types of enthalpies can often be related to intermolecular forces. What you should be able to do after watching this video, you should be able to describe how different types of enthalpies are just changes in enthalpy for a specific process. Given a process, you should be able to determine the change enthalpy of that process using the tables of the different types of enthalpies. You should be able to put a series of compounds in order of increased enthalpy of vaporization based on intermolecular forces. You should be able to put a series of ionic solids in order of increasing last enthalpies and in order of increasing melting points based on the strength of the ion-ion interaction. And so here's a list of different types of enthalpies. They all represent a specific type of chemical reaction. And so the subscript tells you what kind of reaction, except for the R. The R is general, it just means enthalpy of a reaction. F corresponds to enthalpy of formation, and so that's where you're going from elements in their standard state to 1 mole of the product. VAP corresponds to enthalpy of vaporization, you're going from a liquid to a gas. FUS, enthalpy of fusion, you're going from a solid to a liquid. C, enthalpy of combustion, so a combustion of 1 mole of a compound and oxygen. L is the lattice enthalpy, you're going from ionic solids to the gaseous ions. HYD is hydration, you're going from gaseous ions to aqueous ions. SOL, enthalpy of solution, solvents plus solute gives you the solution. And B is the bond enthalpy, you're going from a molecule to fragments where you're breaking a single chemical bond. That's kind of interesting. Some of these enthalpies are always positive, some are always negative, some can be either. And so enthalpy of reaction can be either positive or negative. Enthalpy of formation can be either positive or negative. Enthalpy of vaporization and fusion are always positive. You always have to add heat if you want to go from a liquid to a gas, or if you want to go from a solid to a liquid. Enthalpy of combustion, that's always negative because heat will go from the system to the surroundings. Lattice enthalpy, always positive. Enthalpy of hydration, you're going from gaseous ions to solution, from something less stable to something more stable, and so that's always going to be negative. Enthalpy of solution can be positive or negative. Bond enthalpy, always positive. It always takes heat to break a bond. And so you need to be able to understand and use all these different types of enthalpies. And again, you should know which ones are always positive, which ones are always negative, and which ones can be either. And so enthalpies of formation are the change enthalpy when 1 mole of a compound is formed from elements in their standard states. And so if you remember, we could not determine enthalpy of a compound in absolute terms. And so we define elements in their standard state as 0 enthalpy and measure everything relative to that. And so if you take the elements in their standard state and you form 1 mole of the compound, the change enthalpy for this reaction is going to be enthalpy of the products. So enthalpy of formation of the compound minus enthalpy of the reactants, which, because they're elements in their standard state, would be 0. And so that's how we get enthalpies of formation. And so this gives you a table of some enthalpies of formation. And enthalpies of formation can be positive or can be negative. In general, the more positive enthalpy formation, the less stable, the more reactive. The more negative the enthalpy of formation, in general, the more stable. And so we can ask, what is the change enthalpy for the following reaction, going from H to a liquid to H to a gas? And so again, we can determine change enthalpy for a reaction by doing the products minus reactants thing. And so our gas is the products. The stuff on the right is always the products. Stuff on the left is always the reactants. And so we have minus 242 minus 286. and this gives us 44 kilojoules. Now, if we look at this reaction, we're going from a liquid to gas, and so that's actually going to be an enthalpy of vaporization. And so enthalpy of vaporization is how much heat is needed to change 1 mole of liquid into the gas. Now, if you look at a table of enthalpies of vaporization, you'll see that the number is a little bit different, because here we have the standard enthalpy of formation, and that's defined at 25 degrees Celsius, but typically enthalpy of vaporizations are defined at the boiling point. And so enthalpies of vaporizations are always change enthalpy for a liquid going to a gas. The enthalpy of the gas is always greater than liquid, and so enthalpies of vaporization are always positive. Enthalpies of the solids are always less than the enthalpy of the corresponding liquid, which is always smaller than the enthalpy of the corresponding gas. And so here are some enthalpies of vaporization and boiling points. And typically the larger the enthalpy of vaporization, the higher the boiling point. Typically the stronger the intermolecular force, the higher the enthalpy of vaporization and the higher the boiling point. And so for these top three, the only intermolecular force we have there is London dispersion. For the bottom four, there's hydrogen bonding. Remember, hydrogen bonding is typically 20 kilojoules per mole versus London dispersion, which is like 2 kilojoules per mole. And so the ones with hydrogen bonding have higher enthalpy of vaporization and a higher boiling point. Enthalpy of fusion is going from a solid to a liquid. And so you'll always have to add a heat to go from a solid to liquid. And so enthalpies of fusion are always positive. You can also think about it because the enthalpy of the solid is always going to be less than the enthalpy of the corresponding liquid. And so if we go bigger number minus smaller number, that would give you a positive enthalpy of fusion. And if we look at the table of these, again, the stronger the intermolecular forces, the larger the enthalpy of fusion and the higher the melting point. And so again, the top three are just London dispersion. The bottom four are hydrogen bonding. And so the bottom four have higher enthalpies of fusion and higher melting points. And so if you want to go from left to right on this diagram, you have to add heat. It's always going to be endothermic. If you go from right to left, it's always going to be exothermic, and heat will always be a product. And so enthalpy of fusion, amount of heat required to convert 1 mole of a solid to a liquid. Enthalpy of fusion, always positive. Enthalpy of vaporization is the amount of heat required to convert 1 mole of liquid to a gas. Enthalpy of vaporization is always positive. You can also talk about enthalpy of sublimation, which is going from a solid to a gas, and that would also always be positive. Now, if we look at this reaction, we have methanol plus oxygen goes to CO2 plus water. Now we can calculate the change enthalpy by products minus reactants. And so remember that, so the one on the right is the products, the one on the left is the reactants. Those coefficients always come down. And using these values, we get minus 727 kilojoules. Remember, because oxygen is the element center state, its enthalpy of formation is 0. Now, if we look at this reaction, it's actually a combustion reaction. And so combustion, you're always producing heat, and so the change enthalpy will always be positive. So the change enthalpy will always be negative because heat's coming from the system to the surroundings. And so we just calculated the change in, or the enthalpy of combustion of methanol. So enthalpy of combustion is a change in enthalpy when 1 mole of something is burned in oxygen gas. If the compound is burned contains carbon and there's enough oxygen, then you'll produce CO2. If you don't have enough oxygen, then you'll just produce carbon monoxide. If the compound burned contains hydrogen, then liquid H2O is produced. And so if this is the fuel and you know you have enough oxygen, then that tells you you're going to produce CO2 gas and H2O liquid. And so these are some combustion enthalpies. Again, that's the C. And they're always negative because you're always producing heat. Lattice enthalpy is the enthalpy required to convert ionic solid to gaseous ions. And so you're going from an ionic solid with a strong ion-ion interaction to gaseous ions. And typically in a gas, we assume intermolecular forces are negligible. And so you're going from something more stable to something less stable. And so you're going to have to add heat. And so lattice enthalpies are always positive. The ionic solid is always going to be more stable than the gaseous ions. And remember that the lattice enthalpy is a measure of the strength of the ion-ion interaction. And so the stronger the ion-ion interaction, the larger the lattice enthalpy, and typically the higher the melting point. And in terms of ion-ion interaction, the most important consideration is the size of the charges, the absolute size. And so magnesium is a +2, oxygen is a -2. Calcium +2, oxygen -2. And so they have the biggest lattice enthalpy, highest melting point. Magnesium fluoride, magnesium chloride, you have a +2 and a -1. And then the ones in green are +1 and -1 ions. And so most important consideration is the absolute charge of the ions. The secondary consideration is the size, the physical size of the ions. And so the smaller the ions, the closer the ions, the stronger the interaction. So you could be asked to put compounds in order of increasing lattice enthalpy. And so we first look at the charges. And based on the charges, we see that magnesium oxide, strontium oxide are +2, -2s. Magnesium fluoride +2, -1. Sodium chloride, potassium bromide +1, -1s. And so this is the order we get from based on the absolute charge. Now we have to think about, okay, what about the size? Well, magnesium is smaller than strontium, and so magnesium oxide should have a higher lattice enthalpy, higher melting point than strontium oxide. KBr is bigger than sodium chloride, and so it's going to have a weaker lattice enthalpy and a lower melting point. So first we put an order of absolute charge. Second, we put an order of smaller ions, closer ions, stronger interaction. And again, if we do it in terms of lattice enthalpy or in terms of melting points, it should have the same trend. And so for ionic solids, the larger the absolute charge, the stronger electrostatic attraction, larger lattice enthalpy, higher melting point. Now, if you have the same absolute charges, the smaller the ions, the closer ions, stronger electrostatic attraction, larger lattice enthalpy, highest melting point, but the charges are the most important consideration. Enthalpy of hydration is the change enthalpy when gaseous ions are dissolved in water. And so for gaseous ions, we imagine that intermolecular forces are negligible. Aqueous ions, we're going to have the ion-dipole interaction. And so the aqueous ions are more stable. And so if you're going from something less stable to something more stable, typically you'll release heat. And so the change in enthalpy should be negative. So enthalpies of hydration are negative. Now, if you add enthalpies of hydration, you can actually get, for sodium plus ions, chloride plus ions, going to sodium aqueous ions and chloride aqueous ions. Again, that's just an illustration of Hess's law. Now, if we think about the ion-dipole interaction, and so if the dipole is just due to the water, it's not changing. And so you can think about it in terms of charge and size. So the bigger the absolute charge, the more negative the enthalpy of hydration. The smaller the size, the more negative the enthalpy of hydration. And so the +2 or -2s are going to have a more negative enthalpy of hydration than the +1s or -1s. And so first, absolute charge, second in terms of size. And so if we have sodium in water, it will be surrounded by the oxygen end of the water molecule. And so when we're talking about enthalpy of hydration, it's a measure of all the ion-dipole interactions. Remember, for the ion-dipole interaction, it's like 150 kilojoules. Actually, it's 120 kilojoules per mole. That's for one ion and one polar molecule and one water molecule. The hydration enthalpy is a measure of all the ion-dipole interactions, and so it's going to be a little bit different. And so the hydration enthalpy of sodium is minus 444 kilojoules per mole, versus for one interaction between one ion and one dipole, it's 120 kilojoules per mole. And so again, you can see the sodium is going to be attracted to the oxygen side of the water molecule. As they get closer, it gets more stable. If they get too close, then it gets very unstable. Now, if we flip around the water molecule, we see that we get a repulsion between the sodium ion and the hydrogen side of the water molecule. Remember, the stronger the attraction, the lower the energy, the more stable. The stronger the repulsion, the higher the energy, the less stable. And so what we're seeing here is repulsion, and it's going higher energy, and so it's being less stable. And again, for aqueous ionic solutions, larger absolute charge, stronger the ion-dipole interaction, the more negative enthalpy of hydration. Now, if they all have the same charges, you look at the size, the smaller the ions, the closer the ions to the water molecule, the stronger the interaction. But the charge is the most important consideration. This is very similar to the ion-ion interaction. And so we could put the following in order: decreasing enthalpy of hydration. And it says decreasing, so that's going to more negative enthalpy of hydration, which corresponds to stronger interaction. And so of these, the aluminum should have the most negative enthalpy of hydration because it's got the biggest charge. And the lithium and the chloride should have the least negative enthalpy of hydration. And so first we do it in terms of charge. And now in terms of size, the lithium is smaller than the chloride, and so the chloride should have the least negative of all the enthalpy of hydrations. And so it is. And so this gives you the enthalpy of hydrations. Again, enthalpy of hydration is always negative. And so we can determine enthalpy of hydration for individual ions. Again, the stronger the ion-dipole interaction, the more negative the enthalpy of hydration. And then enthalpy of solution is the change enthalpy when something dissolves in something else. And so you can imagine you're going from something to pure stuff to a mixture. And so you have a solvent-solvent interaction, you have a solute-solute interaction, and then you're replacing those interactions with a solute-solvent interaction. And so often we say likes dissolve likes because these interactions have to be similar. Because if the solute-solute interactions are really strong, much stronger than solute-solvent interaction, then it will never form a solution. But enthalpy of solution can be positive or can be negative.
We can imagine the process of mixing two liquids as occurring in 3 steps. First, the intermolecular forces of one liquid are overcome. We can then think of the liquid as being converted to a gas in an endothermic process. Next, the same thing occurs to the second liquid. Finally, these two gases condense together, releasing energy. The energetics of the overall process depend on the relative strengths of the intermolecular forces involved.
And so it comes down to just the relative energies of the solute-solute interaction, solvent-solvent interaction, and solvent-solute interaction. And so if we look at going from ionic solid to aqueous ions, you're going from the ion-ion interaction to the ion-dipole interaction. And so the ion-ion interaction, can be really pretty strong. I think it's typically like 200 kilojoules per mole. The ion-dipole interaction can be pretty strong, like 150 kilojoules per mole. And so they actually can be pretty comparable. And that's why ionic solids dissolve in water, because of the ion-dipole interaction is strong enough to replace the ion-ion interaction. We can actually calculate the enthalpy of solution for ionic solid. And so we have the lattice enthalpy going from the solid to the gaseous ions. And then if we take the gaseous ions and we put them in solution, forming the aqueous ions, this is the hydration enthalpy. Now if we add these two reactions, you notice the gaseous ions will cancel, and we'll get the sodium chloride solid going to sodium ions and chloride ions. If you add reactions, you add the corresponding delta H's. And so we get an enthalpy of solution for this mixture of 3 kilojoules per mole. And again, remember, it's Hess's law says that if you add reactions, you add the corresponding delta H's.
The dissolution of potassium fluoride can be thought of in 2 steps, although the reaction does not really occur this way. First, we imagine the potassium and fluoride ions separating. This is an endothermic process. Then the ions are hydrated. This is an exothermic process. The combination of these 2 energies is the enthalpy of solution.
And so for some onyx solids going to aqueous ions, you'll find the enthalpy of solution is positive. For others, you'll find it negative. And so for potassium fluoride, it's 2 kilojoules per mole. We found for sodium chloride, it was 3. But sometimes it actually does come out negative. For potassium fluoride, it actually gives you a negative enthalpy of solution. But again, please remember onyx solids dissolve in water because of the strong ion-dipole interaction is able to replace the ion-ion interaction. And so if we look at solubility as a function of temperature, it's really kind of interesting. Sometimes we'll see that something's going to be more soluble at higher temperature, and sometimes you'll see it's going to be less soluble at higher temperature.
A solution of sodium acetate in water is in a flask. A few small crystals of sodium acetate are placed on the top of the laboratory bench. The solution from the flask is poured over the crystals. As the solution contacts the crystals, its color changes from clear to white very rapidly, and it crystallizes into a solid mound of material that builds up into a fairly tall vertical structure. The probe from a digital thermometer touches the solid sodium acetate to test the temperature. It is seen that the material is quite warm. The process of crystallization is an exothermic process in which heat is given off to the surroundings.
And so a supersaturated solution is unstable, and that's why when it's poured on that sea crystal, it immediately crystallizes. So the movie illustrates the sodium ions and the acetate ions go into sodium acetate solid. Now, if we think about enthalpy of solution, that would be the sodium acetate solid going to sodium ions plus acetate ions in solution. And so if we have the enthalpy of solution, that would be endothermic because we have to add heat. Now, this reaction is actually used for heat pads.
Now, a commercial application of this crystallization process is shown. A metal disc is manipulated inside a sealed plastic bag holding the sodium acetate solution. This causes the sodium acetate to crystallize. The digital thermometer shows that the temperature of the heating pack has gone up significantly from room temperature.
And so the
This heating pack provides an easy, portable method of having heat available whenever and wherever it is needed.
So the enthalpy of solution is negative because, it's positive because it's endothermic, but the heating pad uses the opposite reaction, and that opposite reaction would be exothermic. Gases dissolve in solvent, and that is actually exothermic. Hence, they're more soluble at a low temperature. And so gases, typically intermolecular forces are negligible. The dissolved gas will have a Lund dispersion interaction or a dipole-induced dipole interaction because the water is polar. And so if you look at the solubility as a function of temperature, it actually gets less soluble as you raise the temperature. And that's why soda pop goes flat in warmer temperatures, because the CO2 is going to be less soluble at warmer temperatures.
When a can of soft drink is opened, a whooshing sound is heard, and the solution begins to release bubbles. The escaping gas is carbon dioxide. Henry's law explains why the gas leaves the liquid only after the can is opened.
And so Henry's law just says that the solubility of the gas in solution is equal to a constant times the partial pressure of the gas. And so that means that the solubility of the gas in solution is going to be linear with pressure of the partial pressure. So as you increase the partial pressure, you're increasing the solubility. Now, the slope of this line actually depends on the strength of the dipole-induced dipole interaction. And so oxygen is bigger, and so it's going to have a stronger dipole-induced dipole interaction with water, and so it's going to be more soluble. Helium is pretty small, and so it's kind of a weak dipole-induced dipole interaction. If we look at a wider range of gases, again, the bigger gases will have a stronger dipole-induced dipole interaction and will be more soluble in water. And so soft drink is made by dissolving CO2 at 3 atmospheres at 20 degrees Celsius. How many moles of CO2 are in a 355 milliliter can of soda? And so for CO2, we have the constant as 2.3 times 10 to the minus 2 moles per liter per atmosphere. And so we can use the solubility, the Henry's law equation here. And so this is the constant, this is the partial pressure, and so that gives us the solubility of that. And so that's the moles per liter. Now, 355 milliliters is the same as 0.355 liters. And so that tells us how many moles of CO2 is actually in a can of soda pop. And so the partial pressure of CO2 in the atmosphere is actually 3 times 10 to the minus 4th atmospheres. Much, much smaller than inside the soda pop. And so hopefully you can describe how different types of enthalpies are just changes in enthalpy for specific processes. Given a process, you should be able to determine the change enthalpy of that process using the tables of different types of enthalpies. Hopefully you can put a series of compounds in order of increasing enthalpy of vaporization, enthalpy of fusion, boiling point and melting point based on intermolecular forces. Hopefully you can put a series of ionic solids in order of increasing lattice enthalpies and melting point based on the strength of ion-ion interaction. I hope that was helpful.